So I'm going to talk today about, again, something a little bit different concerning graph ensembles, which is a direct result of some other research that I and my team have been working on. Okay, what button do I press? This one? There we are. All right, so I'm going to talk about, first of all, maximum entropy analysis on flow networks, just a summary of work that has been conducted in our group, particularly by my student Stephen Waldrop here on flow networks, and some examples. Then we're going to talk about priors on graphs and go through some calculations of those. And then a few other things, talk about distinguishability and so forth. And I thought you'd like this. The British universities like these trigger warnings, I've heard. So the first trigger warning is that this lecture contains mathematics. And if ever that's brought into the Australian system, this is going to be my warning on every one of my lectures. But actually, the mathematics here is going to be mostly 17th century mathematics, in fact, very similar to some of these classical works. But the second warning is that it does contain some elements of, and I'm destroying the language here, frequentistism, but no Bayesian is harmed in this process, and you'll see why I'm doing it. And it's actually an example where sometimes you do have probabilities that are frequencies, and in which case you use it. So now some work by myself and others. Many people, of course, are working in this area now. This is what I'm concerned with, is a flow network. So where you have a graph structure, a network structure, and you have flows on that structure. And so this can concern, for example, electrical networks, fluid flow networks, pipe flow networks, transport networks, and so on. And even you can conceptualize financial networks and human networks this way. And so it gives you a framework for dealing with many different types of systems. And you'll notice the pretty pictures here. On the left is an undirected graph structure, and on the right is a directed graph structure. And so when you consider undirected graph networks, the way we've been approaching this is we're interested in the flows on the network, but generally you're dealing with, in this case, with potential flows. So, but the way that we've handled this is by considering the unknowns as the flow rates, both within the network and also external flow rates to or from the network. And so we define our probability over those flow rates, so they become the uncertainties. And so we use this relative entropy function as shown. And then the potential differences are handled as implicit variables via the use of resistance functions. And that's a nice framework because you can unify many different types of systems that way. And so there's the entropy. You apply constraints. You have normalization, of course. You have some known moments, which might be measurements of some of those flow rates and potential differences. And you've got Kirchhoff's laws. Put it all together. You get your probability. And one of the interesting facets of this is you have, oops. Let's see if I can work this laser. This one. You have some non-linearities, the possibility of non-linearities here, and that's taken us a great deal of time to be able to figure out and to resolve. And so here's an example of a water distribution system in Canberra, a bit more than 1,000 nodes. So here is the configuration of the network. So here's the green are land boundaries, and the network is shown in these various colours. So these are water pipes to houses. And by using the MaxEnt algorithm, you can do scenario analysis and all kinds of things. So you can do experiments that you can't do in real life. So you could model, for example, what happens if there's a pipe rupture somewhere or whatever. So there's many possibilities of applications. Similarly, you can analyze electrical networks. And again, this is just an example. And for this particular case, we were able to obtain the data just from Google Maps. And it's not really clear on this picture, but there are some photovoltaic systems. So this is a supply to a small part of a suburb. There's some photovoltaics, and under a particular forcing condition, you have reversal of flow, which is in our sort of highly centralized electrical networks now, that's a big no-no. We've also looked at directed graph networks, so transport networks, and these are a bit more complicated because you don't have potentials, and so you have to introduce some more complicated ways of being able to model demand. One of the ways is through this gravity model, as it's called, where you have probabilities. These T's are just flow rates, but they're trip flow rates, so they're flow rates for an entire trip from an origin to a destination. And this is traditionally how these things have been handled in this field, in transport engineering, but what we've done is put this into a probabilistic framework, in which it wasn't previously. So in this particular model, you have mean flow rates between origins and destinations, you have a cost function, you go through the algorithm, and it gives you a result. There are more complicated models which involve or can involve the handling of trip flow rates, path flow rates, and flow rates on individual links or individual roads, if you like, and also some fairly complicated or simple to very complicated schemes for route assignment. So how do you choose a route? Okay, so this then brings me to the extended problem. So you think about a network. We've been just analysing flows on a network, but there are many other properties of the network that we could bring into this analysis. So we could bring in different types of flow quantities. We could have some metric quantities, distances. We could have storages at nodes, so car parks, for example. You might be interested in the node conductivity, so for example, traffic light behaviour. And so all of this kind of thing can become part of your model. And particularly also, the graph structure itself could also be uncertain. And so when you have your uncertainties, as we know from probability theory, there are uncertainties. You write a joint PDF over your uncertainties, and then that gives you this entropy function. And what I've done here is subdivide them, the properties between what I'm calling the flow properties, the physical properties, and also the properties of the graph structure itself. And so that leads me then into this consideration, particularly here, of how do we do MaxEnt over graph structures. And if you go through the physics literature, there's been an explosion in interest in this field over the last 20 years. And a lot of famous names that I've shown up here. But what's interesting is that almost all of these studies invoke a Shannon entropy over a graph ensemble, as they would call it. And what I'm going to do here is just argue for the use of this relative entropy function, this one here, with a graph prior. So now what we have are graph macrostates, which when you define this mathematically, they're just equivalence classes of graphs that you've defined in some way. And then in order to do that, to make it all work, you need your priors for each of those macrostates. So the idea is that I'm proposing here is you actually do your statistical mechanics. So rather than counting each graph. And a nice definition of combinatorics, of course, is the art of counting without actually counting. And so here I'm, if you like, I'm boldly going forth and doing this analysis so that nobody else has to do it again. And so graph priors, well, how do you derive a graph prior? And this is nice frequentist probabilities. So you just consider your ensemble, you choose a particular graph ensemble, you choose a particular way of partitioning that ensemble into your macrostates, and then you do your counts. And so you just have a degeneracy, which is a count of that macrostate, and then a count of the number of graphs in the whole ensemble. So it's nice, it all works. Of course, one difficulty is there are many ways of choosing a graph ensemble and then many ways of partitioning it. So here's an example. So these are undirected graphs with 4 nodes. I haven't labelled the nodes, but I'm implicitly assuming that the nodes are labelled. And they're simple, so there's no self-loops in these particular ensembles. So there's ensembles, you can count them. This is the total number of graphs in that ensemble. And we can partition that according to numbers of edges. That's shown there. That's nice. Or we could, if we're not interested in edges, we could partition it by the degree structure of the graphs. And if you sort of flick back and forth, you see this is actually turns out to be a subpartition of the previous one. And so some terminology. You've got to invent some terminology or you'll get yourself very confused. So undirected graphs are U's. Directed graphs, I'm calling with the symbol D. Nodes, I'm using the symbol capital N or small n, and edges, M. A simple graph has single edges with no self-loops. If I have this sort of circular symbol here, that implies that that particular system has self-loops. And a multigraph, I'm just going to use a squiggle to designate that, so there's a possibility of parallel edges. I'm going to assume, at least for the first set of analyses, that the nodes are labelled, so they're distinguishable, but there's only one type of edge, and when you have parallel edges in a multigraph, that we're not individually labelling each of those edges. Of course, you can do it any other way that you wish. So here's the sorts of things that you get into. When you think about this, so the first example are simple undirected graphs with M edges and N nodes. And so our ensemble is the whole set of these. And I'm going to pick on macrostates that have M, capital M edges. And so when you think about this, you think of the adjacency matrix. And what we're doing is we're allocating balls in boxes. So this is, again, this is very good classical combinatorics. And how many ways are there to form these graphs? Well, we've got capital M balls representing ones, which we can allocate to, this is a triangle number, or the n-1th triangle number. So in that triangle, so there it is there. That's how many there are. We can count those, we can sum over all possibilities of numbers of edges, and that gives us our total, and therefore we can derive our prime. So, simple. And then I've now got a lot of slides where I'm just repeating this same methodology to different choices of ensembles and macrostates. So if you now consider the possibility of graphs with loops, then you can build this up in several different ways. Here what I've done is I've kept this allocation of these balls here to this upper diagonal of the matrix, and we've also have the possibility of L loops allocated to these N elements, and we can do our total, and then we can recover our prior in the same methodology. Or similarly, we don't have to do it that way. If we're not interested in distinguishing between the edges and the non-edges, sorry, the loop edges and the non-loop edges, then we can do it this way. We can just allocate directly to the upper diagonal and, sorry, the upper triangle and the diagonal. Or we could construct it with this allocation scheme, but can now consider all combinations adding up to capital M of edges. And there we are. We know our total already, and there's our prime. For directed graphs, digraphs, we have the possibility now these lower triangle elements are independent of the upper ones. I'm considering without loops in this case, so we now have an allocation scheme of these M edges to all of these. So there it is. And we can add that up as well and get our prime. Similarly, if we're concerned with self-loops, graph with self-loops, then we can include those in the same kind of scheme. Or if we're not interested in distinguishing the loops and the non-loops, then we can just do it this way over the full n squared. Okay, all right, so there's a few examples. Now what we can do, these examples were all for ensembles with a fixed number n, capital N, of nodes. What we can do then is take each of those and embed them in a higher order structure where you've got an ensemble of graphs of any number of nodes up to capital N. And so you just sort of build them up like so. And then you can do some even further tricks like take capital N to infinity and proceed accordingly. So when you do that, what you get is a whole bunch of priors for different examples. This is again just examples of the undirected graphs. What we can also do is consider multigraphs now. So instead of having one edge between maximum one edge per element, you now have an allocation scheme where you can have you can basically put all of these m elements into one of these or any other combination in between. So you have an allocation scheme that does not have any restriction on occupancy, which is very similar to the Bose-Einstein system. So you can work this out. Here's your degeneracy, here's the total, here's your prior. And this particular example has some asymptotic limits. And these are rather strange and interesting. And it turns out that so just stepping through these quickly, capital C is the total number of edges that's allowed in this system. Otherwise, you'd just end up with graphs with infinite numbers of edges. Now, if your numbers of edges in this prior is less than this capital C, the total, then that's asymptotically vanishing. On the other hand, if it's equal to C and C is some small number, then that comes to dominate the ensemble. So in other words, it's dominated by graphs with the maximum number of edges. On the other hand, there's this strange limit here that if this capital C is of the order of your triangle number with some alpha, and you're considering macrostates with that capital C, numbers of edges, then you can develop some fractional limits, which is very interesting. There's some sort of peak in the distribution here, asymptotically. Similarly, you can do the same thing with digraphs. So the mathematics is much the same, except we've got some n squareds instead of triangle numbers. And you can see what I'm doing. I'm just building up tables of possible combinations of macrostates and ensembles, and I'm just going to keep putting out these tables. I know you can't read these, but that's not the idea. We can also partition by degrees, and this is certainly something that the physicists are very interested in. And you can consider in degrees and out degrees for directed graphs, or both of the same for undirected graph structures. And as just some examples, so here's an allocation scheme now. So what I've got here, I should point up this way. So what you've got is you're allocating now elements vertically to a column. So I'm considering out degrees here. So the degree of this node is going to be the sum, a vertical sum down here. But what we have to do is allocate in this column, and that gives a degeneracy in the column, and then multiply columns in order to recover the total degree permutation in this case. We already worked out the total, so there it is. Then you've got to do a few tricks when if you're interested in degree combinations rather than permutations, then you've got to do some accounting for numbers of possibilities. And one way of doing this, I'm not saying it's necessarily the only way, but one way of doing this is if you consider your permutation here, then you consider the repetitivity of the integers in that permutation, and you've got to divide by these factorials of those repetitivities in order to do the accounting correctly. Similarly for graphs without loops and multigraphs without loops, you end up with the same kind of structure coming. And so combinatorics are combinatorics, which can be fun. We can also consider indistinguishable nodes. So going back to this example, if the nodes are not labelled, then each of these is essentially, each of these macrostates then becomes equally probable, because there's no way to distinguish between them. And so you have now a degeneracy of 1, and all you have to do is counting of how many macrostates there are, and there's your prior. Okay, you can also go a little bit further and consider partially indistinguishable nodes. So the example on the left is if you have Danish, written Danish, that's put through an English optical character recognition software, what it's going to do is just all of these other things are going to be just called A's, and this is going to be scanned as an O, and this might end up as an A or an E. And so I've drawn edges of combinations here that can be distinguished, and then when they're missing, they're not distinguished. Another example here, if you're Korean, then there's not a lot of distinguishability in your surnames, as you may have noticed. And I put this slide up at a statistical physics conference a year ago. There were quite a few Koreans there, but I wasn't sort of expecting there to be such topicality in all of these people that I put on the slide. So, but where this is going to go is it's going to go to graph colorings and chromatic numbers and all those delightful or horrible things, depending on your point of view. So to conclude, our group has been working for a number of years now on the analysis of flow networks by MaxEnt. And if you have a flow network with uncertainty in the graph structure, then it's very natural to have this relative entropy function, but then that leads you to consider the necessity of MaxEnt on graphs. The vast bulk, I don't even think I've found a counterexample, but the vast bulk of physics papers on graphs use this entropy function, if they write the entropy function at all. And I'm advocating this with the use of a graph prior, and I'm able to show that you can derive many of these things analytically, which means that nobody else will have to do it again. Okay, thank you.